Okay, so the first thing that you learned in gases, the first general equations that you were introduced to, before you even describe the university content, you first of all had to revise the high school knowledge that you had. You know, a gas is simply a state of matter. You know, these guys have no fixed shape, no fixed volume. They're always in a random motion, and the particles are further apart from each other, but they can be compressed. You have all those physical properties that you discuss on gases. Then the famous equations that you started with is the general one here. So you first of all had this combination of the Boyle's law and the Charles law. So this is the general one. This is the general formula. Then you also had a case where temperature is kept constant. You know when to use these equations, right? So the good part, they will never ask you about this. It's in a rare case that they ask you about you using these formulas here. The fourth one is when pressure is constant. You have T1 is equal to, you have V2 over T2. Now, these equations are all connected in some way. So we just say, we just explain them in such a way that they'll derive. Of course, you're not interested in the deviation of this, but we're just saying the number of moles has a relation as well. So we have a representation of the Avogadro's law with these formulas, and this is the first thing you ever learn to say. There is this guy called the ideal gas equation that you have to learn to use, and you know the P is the pressure, the volume is the V, the N is the number of moles, the R is the universal gas constant, which only depends on the units of pressure given in a question. That's what always determines the R value that you're supposed to use. Here, the universal gas constant. So if a question is given and there's no pressure, you use the first one. You see that the first one here, it has no pressure units. It's just joules per mole per kelvins. But these others here have units of pressure. So if your pressure is in pascals, you use this guy here. If your pressure is in bar or atmosphere ATM, or if it's in tar or millimeter per mercury, so you can decide to use the R that suits the units of pressure in that particular question that you're dealing with. Yeah, so like in this case, we're just saying number of moles is simply directly proportional to the product of pressure, volume, and inversely proportional to the universal gas constant and the temperature. So this is what we have. Yeah, so you know how to use this, right? This is okay. Okay, your theory sheet has loaded. Let me just show it here. Apart from the ideal gas equation, you also learn to say we have these conditions that you are supposed to be relating gases with your mole concept. We have conditions at STP and also at RTP. So you know this is just standard temperature and pressure, and the only thing to know here is that every single mole always occupies 22.4 liters of a container or a vessel. That's at STP, and we always assume that the pressure at STP is 1 atm and the temperature is supposed to be 273, or rather we can just say it's supposed to be, sometimes they say 25 degrees Celsius, which you can convert to kelvins. You know how to convert to kelvins. Your degree in Celsius, your temperature in Celsius needs to be added to 273.15. Yeah, then you convert it. RTP, every single mole occupies what? What's the volume that is occupied at RTP, Nyumezi? This is 24 liters. That's the condition at RTP. Then apart from this, you have to know to say, whenever we are dealing with gases, we have two types of gases that we're interested in. When we just categorize them into two types, we have what you call real gases and we have what you call ideal gases. So real gases are the gases that are affected. So these guys are affected by changes in temperature and pressure and everything else. So these are real gases that we experience from day to day. Ideal gases, these are just in theory. They are not there in real life. Yeah, so we assume perfect gases where the changes that we do to the environment will not affect the behavior of that gas. So if we had that particular gas in real life, we'd have called it an ideal gas, but we're just saying these are practically in theory, they don't exist. We'll have a confirmation of such gases when we talk about phase equilibria in semester 2. There's a topic, phase equilibria, where we talk about the changes that we have in states of matter. So we have something like this. There's a gas, there's a solid, there's a liquid, there's a gas. There's a point that a solid can change and becomes a liquid, then a liquid can change and become a gas. Then when you standardize your pressure and your temperature, so we have pressure this side and temperature down here, there's going to be a point that we call a supercritical point, where any changes you make in the pressure and the temperature will not affect the gas that you have. It's going to be the same throughout. It won't change. But of course, there are cases where we can keep the pressure to be constant, then we reduce the temperature. The gas can actually change and turn back to be a solid. So we have such cases. But here we're just interested in the basic calculations. So this, for now, we'll just stick to the ideal and the real gas part. Then we also have the fact that these gases are able to move. But before we actually talk about their movements, we'll talk about this part here, Dalton's law of partial pressure. So this guy came up with the assumption that there is what we call mole fraction. So mole fraction is just the number of moles of any gas divided by the total number of moles in the vessel where that gas is found. So we're saying if you put gases, let's say you put 3 gases in a vessel like this. This is, let's say, hydrogen, then you have 5 moles of, let's say, oxygen. You are looking for the mole fraction of carbon. This is just going to be the number of moles of carbon divided by the total number of moles. This will be 0.2. You can get the mole fraction of every single gas in a vessel. This will be 0.3. Then the mole fraction of oxygen will simply be 0.5. And to back up his law of mole fraction, he said, whenever you add all the mole fractions of all the gases in a container or in a vessel, they should always add up to 1. That's how you know to say you've gotten the correct things. Is this okay, Nyumezi? You've studied this before, right? Then he came up with the second law of partial pressure. He said, if you add, so I'm using the same thing again. You already have the mole fraction, so I'm just going to put the same vessel previously. Imagine now I'm adding 20 atm of a gas. We're saying that his second law is the partial pressure. The pressure that every gas is feeling is going to be different. Partial pressure of a gas is equal to its mole fraction multiplying the total pressure that we are adding to the system. So if you want to get the partial pressure that carbon is feeling, you have to multiply 0.2 times the total pressure, which is this. And the mole fraction is dimensionless. There are no units. So when you multiply this, you just get 4 atm. The same applies for hydrogen. Hydrogen, you get 6 atm. For oxygen, you get 10. And to back up this, he suggested that the total pressure is equal to all the partial pressures in that particular system. Yeah, so they will give you the total pressure which you added to the system. That's basically what you have. And to just improvise and improve our PV, our ideal gas equation, we know to say, if you are interested in collecting a gas over a particular solution, or let's say water vapor, we always get the pressure we need to use. The total pressure is equal to the pressure that gas is experiencing plus the pressure of the water, or rather the vapor. This is the pressure that we need to use there. But then to do the calculations, we have the total pressure. The volume of the gas alone is equal to the number of moles of the gas. Then you have RT. So this is how we calculate anything regarding gas collected over water or over a certain solution. In short, we're just saying this equation can actually be manipulated. We can relate this with all the other equations we know. It's not limited. We can first of all start with number of moles is equal to mass over molar mass, meaning PV is equal to mass over molar mass, meaning we can make molar mass to be the subject. So Mr. of a known gas is equal to its mass given the pressure times the volume. This is the second version of the formula. Then the other version is PV is equal to nRT. You know already that number of moles is mass over Mr. then I can divide everything by V. That's going to be mass over V with the meter down. Then you have RT. You know that this is going to be density, RT over meter. So meaning pressure can also be equal to this. This is the third equation that you can create. Density, universal gas constant, the temperature over the molar mass is equal to the pressure. So you can just play around with this. Then you also know, I must add this other one, though people neglect it a lot. RT, you know what concentration is. Concentration is number of moles over what? Over volume. So you already know, you can simply say pressure is equal to concentration, RT. This right here is what we call Henry's law. This is, but you guys don't have it this year in your course outline, if I remember very well. So this can also be used if you're given the concentration and they're asking you for pressure of a gas. Yeah, so this can also happen. Yeah, then apart from this, we're just saying these gases are going to be in motion. They're going to be moving. So we need to be able to calculate their speed, right? There's what you call rate of effusion. You know the difference between effusion and diffusion, right? What's the difference? So if you have, yes, exactly. So if you have two gases, let's say gas A and B, these guys are competing, let's say C, they are competing to pass through this tiny opening here. So the lightest gas, the one that has a smaller molar mass, is the one that's going to win the race. So we just say the rate is equal to, we can start with first of all the normal one. The rate sometimes can be talked about in terms of number of moles divided by the time, or we can simply get the root mean square velocity, which is just equal to 3 RT over the capital letter M. M is molar mass, but notice that M has to be given in kilogram per mole. Instead of grams per mole, we have to use kilogram per mole for us to be able to get our root mean square velocity in, this is given in, the units is meters per second. It's just velocity, like the one in physics. Yeah, so this is for one gas. If you're looking at calculating the speed of one particular gas. But if you're doing a comparison, we say the rate of, let's say, gas A, then over the rate of, let's say, gas B. This is equal to the meter of gas B. This is B there, then the meter of gas A. This is when you're doing a comparison between two gases. And it should be logical that the heavier the gas, the more slower it is when it comes to moving. Yeah, so if the meter of B is greater than the meter of A, it means A is faster than B. So you need to expect that. So your calculations must be able to make sense. Yeah, so this is literally what you just have to know on gases, the calculations. The rest, of course, there will be a few things in terms of just manipulating them to see if you'll be confused or not. So to do that, we'll simply do your tutorial sheet. So I'll run through everything that you need from your tutorial sheet. So look at question number 3. Question 3, they are simply saying the ideal gas law states that the product of pressure and the volume of 1 gram molecule of an ideal gas is equal to the product of the absolute pressure of a gas and the universal gas constant. Determine the volume occupied by 2.3 grams of carbon dioxide at STP. So this is, the mass has been given. Carbon dioxide, you know the meter is what? 44, right? Roughly 44 grams per mole, right? STP, you know to say the number of moles is 1. Then you know to say the volume is supposed to be 22.4 liters. That's what you know. So now we can just go and say the pressure, they're asking for the volume, right? Determine the volume. So here we can don't even complicate things here. They're asking for the volume. So we know at STP, every single mole occupies 22.4 liters. So what is the number of moles here? The number of moles of carbon dioxide will be the mass over the meter, which is just going to be 2.34 grams divided by 44 grams per mole. So you get the moles here. Once you get your moles, you put the moles here and get your x. Yeah, so try punching this. What is 2.34 divided by 44? So if these are the moles that you're getting, 0.053 moles, then multiply it by the 22.4. 1.1. Okay, so just say 1.1 liters, right? We're looking for liters, isn't it? We're looking for the volume. So this is going to be the volume. So that's basically what you need. Is this okay, Numes? Are you following? Then the second question, they are saying, at what temperature will 0.654 moles of neon occupy 12.30 liters at 1.9 atmospheres? So here we are given enough information for us to get our temperature, and we know to say by the time we are done, our temperature has to be in kelvins. So this must be straightforward. In terms of the pressure has been given, the volume has been given, the number of moles has been given, the R we know. So just do the replacements. Pressure is 1.95. So in your working, make sure you show your units so that you see the dimensional analysis happening, all the units cancelling out. 12.30, this is liters. Number of moles, you are given 0.654. These are moles. So because of space, I won't show the units of the R value, but we're looking for temperature. So because the pressure is in atm, on our formula for atm, the R should be 0. Is it 0.8206? Okay, so we have this part here. We have our nitrogen gas. They are saying calculate the volume of our nitrogen gas. So let me just rewrite it separately. So we have, let me open it from here. So number 4, we are told the nitrogen gas. So according to this question 4, they've given us sodium azide, which has a mass. The mass is given as 125. That's a mass of the whole thing, but we're just interested in getting, the question is specifically asking for the volume of nitrogen gas at T. So the temperature is given, the temperature is the same, 27 degrees Celsius. Then the pressure is given to be 756 star. That's the total pressure of the whole system. Then they're asking for volume again. Yeah, so okay, we're asking for this. So we're saying the pressure times the volume is equal to the number of moles. So this is for the nitrogen. We need to put nitrogen there, then RT. So the pressure is for the whole system. We have it is 756. Then we're looking for the volume. The number of moles of sodium, sodium azide, but we're just interested in the number of moles of nitrogen alone. So we know to say in the sodium azide, what will be the mass? What was the mass of nitrogen? So we're going to get the mixture of sodium azide. This is going to give us 3 by 14. Then this is 1 by 23. So if you get this, that gives you what? This is 2. That's a 1. That's 42, 23. Is this? Are you also getting a 65? That's a molar mass roughly. I'm using the whole numbers one, not the ones that have not the ones that have decimals from your normal periodic table. So from here I'm going to get the mass of nitrogen. So I just want to get the mass of nitrogen. Or in fact, you can just get what you can get. Let me show you a shortcut or the normal way. Nitrogen in this thing is just going to be, it's contributing 42. So 42 out of the 65 multiplied by the total mass. The total mass is 125 grams. So what is the mass that you are getting? It will be 8 point. You are saying 8.76? 80. Okay. 80.76, that's what you're getting. So if this is the mass, that we're having now, we can get the mass of nitrogen alone. So if this is the mass of nitrogen composition in the whole sodium azide, we can now simply do the number of moles. Number of moles will just be the mass, which is 80.76. Then we know to say nitrogen is what? Nitrogen is diatomic, right? So if this is what we're having, then we can just divide by what? This is by 2, so that's going to be 14. That should be a 14 times 2 down. So when you do this, you get the number of moles
as 2.8846.
43.
2.8846.
Okay, so there's 2.88, then with a 4, so I'll just take these guys that I'm able to hear you say, so that we get our pressure is 756. It's in torr. We're looking for volume. The moles are here, 288. The gas constant that we need to use is the one that has torr, which is 62.364. Yeah, so it's 62.364. Then the temperature was given in what? It was already given in this is in what? It was given in degrees Celsius. We have to convert it, so we're adding 273. That should be a 300. Yeah, so here I'm just going to divide by 756, even this side by 756. So meaning we'll get our volume. Our volume will be in liters. So that's what you're supposed to get. Is this okay? Is this okay, Nimezi? So this would be the volume that you're going to get. Yeah, this is. So we're specifically only going to use the total, the normal temperature, and the total pressure. But for the number of moles, we have to be specific. The ideal gas is just for the gas. The sodium is not going to be part of the calculation that we're doing. Yeah, so that's the only thing to be careful of. Then I should have mentioned, I need you to take note of the following equation because of our next question. There is this equation that we use that is called the van der Waals equation. The van der Waals equation is just given as the pressure, the total pressure of the system. Then you have the number of moles. This A is a constant. It changes depending on what you are looking at. Then here you have the volume minus the number of moles. There's a constant again, B. It's equal to nRT. So we have this formula, which is the van der Waals equation. So like our next question here, when they're saying a 1 mole of ammonia fills a 7-liter bottle at 350. What does the van der Waals equation predict that the pressure will be for ammonia having this as the initial, the A constant and the B constant? So you are given these two of them. This is what you are given. So the formula is always going to be straightforward. You just have to plug in. Yeah, and the number of moles will be given. The constants also be given. Only one thing will be missing at a time. Yeah, so we're looking for the number of moles. Yeah, so if we're looking for the number of moles, we go back here. I've given you the formula. This is what you have. So according to the data, if I just open our document, so we're looking for P. That's what we're looking for. So I'll put the P there. So meaning P, then okay. The P is given, so we have the A. The A is also given. A is 4.17. Then the number of moles is 1, so squared. The volume is given to be 7, so 7 again squared. Then the volume is 7, then minus the number of moles, which is 1, times your B, which is 0. This is 0.371. So in your case, you'd have to show all the units. So this is equal to the number of moles is 1. The pressure that we're interested in here, we'll just say it has to be in what? Look at the value of A. A has ATM, so we have to use the one that has ATM, which is just this guy, 0.08. Yeah, so here we're using 0.08206. The temperature is 350. So meaning we're just solving for P. Yeah, so P plus whatever you get here, which is 4.7 over 49. This whole thing is equal to 7 minus 0.0371 is equal to this side when you punch it, 206. Then you're having 350. This is 350. So from here you can just get your value of P. Just make P the subject. Yeah, so you are able to do that, right? Yeah, so this is basically what you're going to get. So your P, if I may just simplify life for you here. So P is supposed to be 0.08206 multiplying 350. This thing has to be divided by 7 minus 0.0371. The answer you get here minus 4.17 over 49. So this is supposed to be your pressure, and it has to be in ATM when you're done. Yeah, so this is going to be your pressure. I've just made P the subject for you there. So the same applies to the next question. The next question is also the same. They've given you the constants as well, so you can just attempt this. They're saying calculate the temperature. Now we're looking for T in the same equation. Yeah, the same equation. This guy here, you have to get used with it. This is going to be V minus NB is equal to nRT. We're looking for T. Everything else has been given. The number of moles, the pressure was given to be 120, the volume was given, the constants are also given. So everything, if they mention a particular gas, every gas has its own constants. Yeah, so they will always give you the constants. So you can try this, and you can let me know what answer you're going to get. Here they want you to compare this value with the temperature you calculated from the ideal. So you also calculate the temperature from this formula. Just calculate it from here. So compare the temperature you get here and the temperature you get here. Which one is big? Which one is small? Is this okay, Nyumezi? Yeah, so this is just okay on the Van der Waals equation. Then here they're simply saying Graham's law of effusion. Here they're saying this equation is on kinetic molecular theory of gases. What is the difference here? We've talked about this. This is through a tiny opening. This is just from a higher concentration freely to a lower concentration. What does Graham's law state? Do you know what Graham's law state?
Yeah.
Okay, so it's almost the same as the expression we had that I gave you for root mean square velocity. So the whole rate of effusion just states that when you're comparing the equation, this states that the rate, you just write this rate, the rate 1 over rate 2 is equal to the square root of molar mass. This same is Graham's law, this guy here. This is the Graham's law. Yeah, it tells us the law of the rate of effusion, their behavior. So this is just writing you this answers this question instead. It states that, or you can just say the rate of effusion, it just states that the rate of effusion is, for one gas, that is, I'm talking about root mean square velocity, is equal to the square root, you write, so just putting the formula in words, the square root of 3RT over what? Over the meter, where the meter has to be in kilograms per mole. That's the only thing that we have to do. So that, but this, I'll just advise you stick with this. Yeah, so this is the basic thing. The rate of effusion of a gas is inversely proportional to the square root of its molar mass. Yeah, of course the constant is 3RT. Yeah, so
For diffusion is not inverted, that's direct.
for what?
In the question asks us to find the diffusion, we just do direct, we don't do the
Oh yes, yes. For diffusion it's direct, yes. Yeah, so then here saying which gas will effuse faster between ammonia and carbon dioxide? you simply check the mister. Just check, this is ammonia, NH3, then this is carbon dioxide, that this is 3 plus 14, that's 17, then this is 44. Which one will refuse faster? Ammonia will be faster because it's lighter than this. What is the relative ratio? So the ratio, just do 17 to 44, then divide by the smallest. The smallest is 17, divide by 17. This will be 1 to a number this side. So meaning, yeah, so if you divide 44 by 17, what do you get?
2.588.
2.9?
2.588.
2.5, okay, 88. So that's the same as 3 if you just round it off. So we're saying ammonia is 3 times faster than carbon dioxide, or carbon dioxide is 3 times slower as ammonia. So this is the ratio that we're going to get. Yeah. Now here they are saying the rate of effusion of a known gas is determined to be 2.9 times faster than the rate of ammonia. What is the approximate molar mass of the unknown gas? You've seen what we've done here, right? We do it in a reverse way. So we don't know. Look at this. We divided by the smaller mass. This is what we're having. Now they are saying the rate of effusion of a known gas is determined to be 2.9 times faster than what? Than ammonia. So if we have ammonia, which is 17, and we have the unknown gas, let's put X. So logically, you're already seeing that that guy has to be faster, meaning it has a smaller what? It has a smaller molar mass, right? So meaning it's the one that we divided. So in short, we just said, if you divide here by X and divide here by X, this should have been 1 to what? To 17 over X. Meaning 17 over X is equal to the 2.9, the 2.92, so we can cross multiply here, meaning X is equal to 17 divided by 2.92. What answer do we get? That will be the molar mass of the unknown gas. 5.82. 5. Yeah, so this will be the molar mass of the unknown gas. Is this okay? Yeah, so here they're just trying to to trick you into using your ratios. Yeah, that's basically what we are having. Yeah, it's not that complicated. They just want to see if you can apply. Then number 8, they're saying to separate isotopes of uranium, the metal is reacted with fluorine to produce UF6. This is uranium, to take advantage of the fact that the different isotopes diffuse at different rates. Determine the root mean square velocities of this guy and this guy at the same temperature. So determine the root mean square velocities of this first one and the second one at the temperature, which is 65. So to differentiate the velocities here, the only way we're going to do so is by using these guys here. Use these as the misters, because that's the only time they will be different. Because if they say velocities, meaning we need to get 2 answers, but they both have the same molecular formula, which is UF6. So UF6 will give you the same answer, but then we're just saying use this and that to get different answers. Because so you say this will be for the 235, you say the same thing, 3RT over the mister, which is the 235, which is going to be 0.235, because we are dividing it by 1,000. It has to be in kilograms per mole. The temperature is the same, 65. Put it in kelvins, you get your velocity there. It will be different from the other guy, which is 238. Because if you use the UF6 and calculate the molar mass, meaning it's the same answer for this and this. I don't know if you're getting what I'm saying, Numezi. That's the only time we will be able to differentiate these guys. Then we'll compare them and also answer the next question that follows when they say determine which molecule diffuses more quickly and determine the ratio of this. So which one? Obviously this guy will be faster because you're using 235, and the ratios just say 235, or you can use the rates. This is 235 to 238. You can just divide this by 235 and 230. So the ratio is going to be very minimal. It will be like 1 to 1 point something. Yeah, that's here we'll be allowed to use the decimal ratio because 238 divided by 235 will be very small, so it will be 1 point something. Yeah, so we have to talk about it in terms of the way it will be. So I mean the other one will just be slightly faster than the other guy. So that's your number 8. Then your number nine, they are saying if a gas is collected over water, what corrections need to be made when collecting the volume of the dry gas at STP? What corrections do we need to make? Does the question make sense to you?
This is about the questions that we talked about when getting water, how we must do the one for density, the one for mass over molar mass.
Yes, so how would you phrase your answer in this context? How can we phrase our answer?
I think I would talk about how to collect corrections to the mass over molar mass and collections over water.
Okay, so the first thing, yes, that we're supposed to do is they're saying when collecting a gas over water and converting the collected volume to dry gas at STP, two main corrections are needed. So the first thing, subtracting the vapor pressure of water from the total pressure, because remember we said the total pressure is equal to the gas that is collected plus the pressure of water, right? So they want us to focus on the dry gas. So when they say dry gas, they mean that it's no longer, we've collected it. It's no longer mixed with water. So it will be wrong for us to use the total pressure. We need to get the pressure off. We need to obviously use this. At some point, we'd have to use this. But then we need to use just the pressure of the gas because it's now dry. It's no longer mixed with the water. So we need to subtract the pressure of the water from the total gas, from the total pressure to get the pressure of the gas. That's the first thing that we need to do. Then they are simply saying, subtracting the water vapor from that. Yes, we've done. Then using the combined law. So we're going to use the combined law of, at STP, you know, to say every single mole occupies what? 22.4 liters. And the pressure of the gas is that. So you're saying if gas, what correction? So we're using the combined law. The pressure is given. So we have what? When calculating the volume, so we'll just use the volume using this. We'll use this formula here, P1, V1. Yeah, so this is what they mean by using the general gas laws. So we don't use the ideal gas, we use this one. Why? Because it's collected, it's now dry, it's no longer mixed with anything else. And we know at STP, the initial thing, we're looking for volume, right? So the initial thing is the pressure will be given. We can say the pressure is standard because it will be given, so I'll just stick to use this guy here. Did they change the temperature? No, they didn't mention the temperature, but we know the temperature is what? Is at 25. This what correction should do. So the first thing is subtracting. The reason that they're giving us here is subtracting. The second one is use the original gas law. That's simply what they are saying. These will be your two answers here. I hope this is okay. We have no need to.
Atmospheric pressure at RTP, or do you know this RTP?
Pardon?
Like you don't just talk about STP. Talk about for RTP.
Or for RTP to be at room temperature and pressure. So at RTP we know. So for this one, they are specific. RTP, a gas will just be in a gas form. There won't be a mixture. The reason why we have this disparity, this water being collected, a gas collected over water, is because at STP, the volume, the conditions are not the same as at room temperature. Room temperature, if something is meant to be a gas, it will be a gas. If something is meant to be a solid, it will be a solid or a liquid. They can't be mixed. But at STP, things can actually be mixed. We can have a vapor and a gas. We can have water and gas. Yeah, so this discussion cannot be held, or we cannot do this comparison on RTP because RTP is just a normal condition of a room temperature.
Okay.
Yeah, so they'll always actually only ask about STP, if anything. Yeah, because at RTP, nothing is unique. Everything is normal. Yeah, so now the last one here, they are telling us to say nitrogen is collected over water, the temperature is given. Determine the partial pressure of nitrogen. If the total pressure is this, the vapor pressure is at this is that. So this is a very logical stepwise question, because you know to say the pressure of vapor, the pressure of the total pressure, we say the total pressure is equal to the pressure of the gas plus the pressure of the vapor pressure. So we can just use the total pressure is 99.42 kilopascals, that's 10 to the power 3 pascals. The pressure of the gas plus, they're saying the pressure of our vapor is simply 738 times 10 to the power 3. So we're looking for the pressure of the gas. So the pressure of nitrogen is equal to 99, let me just use it in kilopascals, this guy minus the 7.38, then kilopascals. So this will give you the what? This will give you the pressure. This is okay, hope this is okay. That's the first one. Then they're asking for the mass of the water vapor in the gas phase. So if they're asking for the mass of the water vapor, meaning we're going to use the pressure of the water vapor to be precise. Yeah, so in the gas phase, so we're just using what they're asking for. So like here we have two, it's like you have two things. It's like you have a gas, which is nitrogen, and you have water vapor. So they're specifically asking for water vapor. So water vapor, we're going to go with, they're saying what's the mass? So the pressure V is equal to, we're saying number of moles is simply mass over Mr. Then we know RT. We know the volume. The volume has been given. Was it given? Did they say the volume? Was it given? No, it wasn't. But they're just asking for the mass. What can we do here, Numes, to get the mass? Because the pressure we do have, the volume we don't. The Mr we do have. The Mr is water, so Mr we know it's 18. R we have this. So what will be the volume? I remember this in your assignment. We say the volume is taken as, so the volume is taken as 1 liter. That's the assumption we take. Yeah, so they should have said here, I think there was the original question, they said assume volume is 1 liter. That's the standard assumption that we are making. Are you following, Numezi? Yeah, we assume it's this. Then from here now, after we assume that is that, we can get the mole fraction. Mole fraction of the nitrogen gas, you have to get. Now mole fraction, this is the easier part. Mole fraction can mean anything. Mole fraction has no units. So you can actually get mole fraction even using pressure. You can just say the mole fraction of the gas, it's just like a ratio. So the mole fraction of nitrogen is equal to the pressure felt by nitrogen over the total pressure of the whole system, because it doesn't have units. So the total pressure, that was the difference between this and that. That's the pressure of nitrogen. You put it on top, divided by the total pressure, which was 99.42. This will give you the mole fraction of water. Then if they say the number of nitrogen molecules collected, meaning you have to get the number of moles first. Yeah, so in short, you use this equation. Pressure is equal to pressure times the volume, 1 liter. Pressure of nitrogen, by the way. The volume of nitrogen, which is just 1 liter. The whole system. The number of moles. Get the number of moles, RT. After you get the number of moles, you know to say 1 mole contains the Avogadro's number of particles. You know this, 23 molecules. So that number of moles you've gotten will give you how many molecules. Then you get to know the molecules of the nitrogen gas that was present. So this is what we are supposed to do here.
Okay.
Is this okay?
Yes, it is okay.
Okay, so now that we've done through this, I think the only weird thing that people don't emphasize is the Van der Waals equation, but now at least you have exposure, you know how it looks like and how to use it. So you can just try to redo these, like try to go through to see if you have challenges. And also the best way to revise is look for similar questions. Let's say if you're using the Dafloid chemistry pamphlet, just look for questions on gases on every paper. Anything that has to do with gases, then try to answer everything. That's how you will revise easily. Yeah, by the time you are done, meaning you'll be revising all the topics. Okay, so this is for today. This is enough. You let me know if you have any questions on WhatsApp, right?
Yes, thank you very much.
All right, sure thing.